Before we begin, I want to thank you for being the best class ever, doing tons of work, helping me out as my daughter's sick. I need to stay at home. I need you to do a lot of work to learn a lot. So pay attention to this video and then do a lot of work, get those calculators out, have those pencils writing, ask each other questions, because a lot of you are going to get this more than maybe some other students might get it, and you can help each other out. But I appreciate all that you're doing, and I will hopefully see you tomorrow. Please learn the Doppler effect from my daddy.
Please learn the Doppler effect from my daddy.
The frequency of this tuning fork is 256 hertz. And so if I play it, it's going to sound something like this right here. And there's no relative motion, so I'm not going towards you or you're not going towards me. You're just going to hear exactly what is given off and also what you perceive, which would be 256 hertz. Now, if I go ahead and make that 256 hertz source go towards you, while it's going towards you, you should hear a perceived frequency higher than 256. So notice, once again, let me get it going again. Higher when it goes towards you, and then lower when it goes away from you. And then the combination while it goes past you. Once again. And then when it's not moving, back to 256 hertz.
Waves and sound. Day 6, the Doppler effect. A person recognizes sound frequency as a highness, ah, or lowness, oh, as a result of compressions and refractions of sound, which is the longitudinal mechanical wave. I represent it in this picture right here as the different compressions right here and refractions right there. Humans can hear frequencies in the range of 20 to 20,000 hertz. This is called audible sound. And a little bit more about the Doppler effect. It's a phenomena that relates to the frequency of a source being perceived different due to the relative motion of the source or the observer. If the relative motion is towards the source, the perceived frequency is higher. If the relative motion is away from the source, the perceived frequency is lower. And so relative motion, both objects could be moving, and there's an equation that will kind of equate what the relative motion would be and what the perceived frequency would be as a result. Okay, if the relative motion, here's another idea of relative motion. If a person is the source and the observer, he's moving the same speed as the source, and therefore the relative motion would be zero, and he wouldn't hear anything different than the normal alarm siren frequency. Before we go any further, I just want to talk a little bit about temperature and how to figure out the velocity of sound in air at different temperatures. And there's an equation. V sound equals 331 plus 0.6 times temperature Celsius. That TC represents temperature Celsius, not period, like we saw capital T in this unit. So TC represents temperature Celsius. Here's an example. If the temperature, in a question we were told the temperature was 10 degrees Celsius, all we'd have to do is plug it into the calculator. Best way to do this would be to multiply 10 Celsius times the 0.6 and then just add 331 to it. So this is the end result would be 337 meters per second. The Doppler effect problems today will often have you calculate the velocity, so watch out if they give you the temperature, because there's a V sound part of the equation you'll see in a few minutes. Watch out for a little bit of human error. If for some reason I've had many worksheets where I forgot to put in the velocity of sound or the temperature, so if you don't get that, ask me, but if I'm not around, you can use 340 meters per second, but be aware, watch out, because if I give you temperature, don't use 340, calculate. So a little bit more about the Doppler effect equation. We'll talk about it a little bit later, but the actual the perceived frequency is equal to the actual frequency times the velocity of sound, that's the sound part of the equation, plus the velocity of the observer, over the velocity of sound minus the velocity of the source. And so that's the whole perceived part of it, the relative velocity part of it that will change the actual frequency. But we'll come back to this equation. Right now I want you to understand what the difference between a source and an observer is. Often that's the difficult part of a problem. So here I have the ambulance being the source. If I play it, I'm going to go back. There's an ambulance. So once again, the source is the ambulance. But the source could also be the person, and so the source here, that's some of my best work. Okay, but there's only going to be one source. It's either going to be the ambulance or the person, because the Doppler effect doesn't allow for two sources. So you're going to have to pick between the source, which one's the source, which one's making the sound, and which one's hearing the sound, and then also decide what their velocities are, or if they're at rest. So let's go back to the ambulance. The observer here is the person who's going to hear that sound. The relative motion of the source or observer would cause a change to the actual frequency, and the observer would hear a different pitch called the perceived frequency. So if you take a look, the relative motion is actually compressing this side, the side closest to the observer, and therefore he's going to hear a higher pitch on this side. So the perceived frequency of the observer is higher as the source approaches the person. And if the ambulance passed the observer, you would hear a pitch much lower. Wow, 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 wow. You would compress the wavelength if you were running towards the ambulance. The perceived frequency of the observer is higher. You would stretch the wavelength if you were running away from the ambulance. The perceived frequency in this case would be lower. Cumulative effect of both running towards each other would be even a higher frequency. So in this case, I have the source driving to the right and the observer running to the left. Relative motion is really what matters. So if the runner is running 3 meters per second away from the ambulance, and the ambulance is chasing him at 3 meters per second, really the relative motion here would be 0, and so the frequency heard would be the actual frequency given off by the ambulance. So let's look a little bit closer at the Doppler effect equation. Here's it written out a little bit further. Perceived frequency equals actual frequency times the velocity of sound plus the velocity of the observer over the velocity of sound minus the velocity of the source. And so it's written down here as F equals FO, FO being the actual frequency, or original frequency, another way to say seeing O there, times the velocity of sound plus the velocity of the observer divided by velocity of sound minus velocity of the source. Now, if you consider if the observer and the source was not moving, those both would not be there, and it's V sound over V sound, or the actual frequency right here, FO, the actual frequency FO would equal to the perceived frequency. So it's just something you can look at. Now, when we use this equation, the Vs and Vo are positive if either are moving towards the other. This is a special equation that we're going to use in this class. You might see other classes using a different equation. I like to be able to see this equation and think, okay, if either is going towards the other, we're going to add a positive value on top of whatever sign you see. We'll still keep the positive and negative signs in that equation. Let me give you an example. But let me just make sure that you get what I'm talking about. VO would be positive if the observer moves towards the source. VO is negative if the observer moves away from the source. VS is positive if the source moves towards the observer. VS is negative if the source moves away from the observer. This is all in addition to the signs you see in the formula. So this is where you really will see what I mean. So let's say, in this case, I didn't use the temperature of the day. I told you the speed of sound was 340, so that's going to be the 340 for V sound. It's going to be on top and bottom. And the source whose actual frequency is 700, so that's going to be that FO actual, is moving 20 meters per second. So the source is moving 20 meters per second away from the observer who's standing on the sidewalk. Now, just thinking about this, if something's moving away from you that's making that noise, you should hear it lower. So when we get a final answer, I would expect to see something less than 700. You should be thinking that way as well, 700 hertz. And here's what this would look like. So this is what I mean. If so, the source was moving away at 20 meters per second. So it was negative here, but we still kept the negative in front of the Vs, so it's a negative negative, and that becomes a positive, or 340 minus, or 340 plus 20 on the bottom, which equals 360. So just being a little bit more spreading that, expanding that out, the actual math here would be 700 times 340, because it's 340 plus 0, over 360. And when I get my final answer, it's 661 hertz, which is what I expected. I expected to hear a lower frequency than the 700. There's some stuff you can do. If you go to the PowerPoint online, you can look in, there's a fun little animation you can watch. Some other uses of the Doppler effect are Doppler radar. It detects the speed, the relative speed of the clouds and the storm fronts moving. Radar guns often will use Doppler radar, and that can include light and laser. Actually, there's such thing as a red and blue shift based on if constellations or things are moving away or towards you. Now let's look at some examples that are actually in your notes. So take a second. If you haven't got out your notes, you might ask the sub to pause this if you're still getting ready. But get out your notes and let's look at examples 20. This is in one of your last sections of your notes. Sitting on a beach at Coney Island one afternoon, Sunny finds herself beneath the flight path of an airplane leaving Kennedy Airport. What frequency will Sunny hear as a jet whose engines emit sounds at frequency of 1000 hertz flies towards her at a speed of 100 meters per second? And here I'm telling you to use 340 meters per second as the speed of sound. So let's take a look at this. I advise you to draw a picture on any of these problems. I like to write as a circle and write down S in it or source in it, and then there's another circle representing the observer. And then I'm going to have arrows that are going to represent the direction of that velocity, because remember, if one's going towards the other, it's going to be a positive. If one's going away, it's going to be a negative, and if it's not going anywhere, it's going to be a 0. So here, the source gets a frequency of 1000 hertz. The observer is getting a velocity of 0 because it's not moving. And the question here is, what is the actual frequency heard? And the V sound for both cases, because I didn't give you a temperature, I went ahead and told you 340 meters per second. This is all information you need right now to solve the problem. This is a givens list. This would be a perfect little picture that you can use. It would help you do the correction correctly. But watch out for the temperature. If you ever get given a temperature and not this velocity of sound, you're gonna need that, and you're gonna have to do one more step, which is V sound equals 331 plus the 0.6 times temperature Celsius. So here's the math. I don't want to spend too much time on it. I'll wait here for a second so you can kind of look at it, copy down what you need. Here the source was moving towards, so it's positive, and so it was a positive, but we still kept the negative. Watch out for that. It's a negative positive or a negative. And then we would expect if it was moving towards it, the frequency would be higher. In that case, it was. It was 1416 and change hertz. And so that's higher than the 1000 of the frequency of the engines originally. Here's another one, but in this case, this is a different question because here we're flying away from her at 100 meters per second. So we would expect the frequency away. That's going to be a bigger wave. That's going to be a lower frequency as a result. And here's the math with that. Here we're given the 100, but this is going to be, now it's source being negative, but it's a double negative or a positive when you do the math. And our answer for this one would be 770. So just take a look, see what you did, copy down what you need to. You're going to get a little practice today. Here we have another question, and I should have drawn a picture on the last one. Let me go and draw a picture here. So we have a source and observer. I'm going to do this before I even read the question. A sparrow chases a crow with a speed of 4 meters per second. Okay, let's find out which one's which. What frequency of sound does the crow hear? So the crow is the observer. Crow, sparrow is chasing the crow. The sparrow chases the crow with a speed of 4 meters per second, so Vs equals 4.0 meters per second. And so that's going to be a positive. Then, and it's chirping the source, so the frequency original is 850.0 hertz. What frequency of sound does the crow hear as he flies away? Okay, in this question, we have a sparrow chasing a crow with a speed of 4 meters per second while chirping at a frequency of 850 hertz. What frequency of sound does the crow hear as he flies away from the sparrow at a speed of 3 meters per second? So you need to really concentrate and think about this. Which one is the observer? Which one's the source? I always like to think which one's the source. So what is giving off that frequency of 850 hertz with no Doppler effect occurring? That's what it would be. The crow hears it. The crow hears it. That tells me that it must be the sparrow that's giving it off. So the source is the sparrow giving off the 850 hertz. The sparrow is flying at 4 meters per second, chasing the crow. So it's a plus 4.0 meters per second. The crow is trying to get away, not doing a good job because he's going at 3 meters per second, and the sparrow is catching up on him. So as the crow's going away, so relative, if it's going away from the other one, it's getting a negative. So the VO would be negative in this case. The VS would be positive 4.0. The VO would be negative 3.0. The frequency original would be 850, but of course, it looks like the sparrow is catching up with the crow, so I would expect this to be a little higher, because relative to the other, one's actually going 1 meters per second towards it. And then the sound on that day, I didn't give you temperature, I just told you 340 meters per second. So this is how you would do it. The VO is a plus VO, so it's a plus, a minus, or just a minus. The VS was positive because the source was going towards, and so it's a minus, a minus. And when all things are done, the actual frequency was 852.53 hertz, which is what I expected to be slightly higher than the 850 because the sparrow was catching up with the crow. So hopefully this helps. Now go ahead and get your work done. Honors has an echo worksheet that I have a key to up front. Do that work. Check your work as you go. CP, I want you to do section 7 of the worksheet packet. The first page looks like that, so you know what to look for. There's section 1 and 2. Don't do that. Do 7. And if you get done with 7, go back and do as many of the other sections as possible. Thank you, and I hope to see you soon. Have a great day. See ya.